So today I'll be explaining about Boyle's law. I will actually be doing problems for one of my moots on Twitter, so hopefully I'll be able to explain well on what Boyle's law is all about. So Boyle's law basically what Boyle's law is, it's just one of the ideal gas laws. Basically what it's saying is that for a fixed amount of an ideal gas kept at a fixed temperature, pressure and volume are inversely proportional. Basically it's a formula. So we have our first pressure and our initial volume, and then we have our final pressure and our final volume. So the very first question that we have on our Boyle's Law practice problems is: you decide to climb the tops of some of the tallest mountains. Before you are about to leave on your epic journey, a friend gives you a balloon with a volume of 800 centimeters cubed that was inflated under standard atmospheric pressure. You climb two different mountains with this balloon: Mount Everest at 29,028 feet above sea level, which has an average atmospheric pressure of 221 millimeters of mercury, and Mount McKinley at 20,320 feet above sea level, which has an average atmospheric pressure of 345 millimeters of mercury. Before calculating any values, predict on which mountain the balloon will have the largest volume, and then what was the size of the volume on each mountaintop. So there's a lot of information given for this very first question, and we should probably break down all the information that we have. So first we have a balloon that has a volume of 800 centimeters cubed at standard atmospheric pressure. Now, standard atmospheric pressure has several different, so 1 atm, for example, that's the standard, is actually equal to 760 millimeters of mercury. Okay, so that's one of the information that this particular question gives us. Now, the next information that we've been given are the two mountains. So we have one mountain, Mount Everest, and we have a second mountain, Mount McKinley. My handwriting sucks, I'm sorry. Anyways, so for our first mountain here, it was, I believe, at 29,028 feet above sea level. And then for Mount McKinley, we have it at 20,320 feet. Now, what's important here is that it's giving us this information first. And as you can see from our formula, there's absolutely no room for altitude. The information that they're giving here is for that first part of the question, where you're predicting on which mountain the balloon will have the largest volume. So based on your lecture that you've been given from your teacher, you should know that as altitude increases, atmospheric pressure decreases. So what we know from here is that Mount Everest has a higher elevation than Mount McKinley. So that tells us that the pressure is a lot less on Mount Everest. Now, from Boyle's law, we know that pressure and volume is inversely related. So when pressure is low, we'll know that the volume is high, and vice versa. When pressure is high, volume is low. So altitude and pressure are inversely proportional, so is pressure and volume. Okay? Now, that's the first part of the question we just answered. So before calculating any of the values, predict on which mountain the balloon will have the largest volume, we just stated that as the altitude goes higher, the pressure goes down, and since pressure and volume are inversely proportional, we know that when the pressure is low, the volume is high. So on which mountain the balloon will have the largest volume, we can predict that since Mount Everest has a higher elevation, that this one will have the larger volume. But let's prove that now by doing some calculations, which is answering the second part of the question: what was the size of the balloon on each mountaintop? Okay, let's use a different color here. Alright, so from this information, we're going to grab our formula. Let's use this other end. Alright, so let's repeat Boyle's law. Where we have our initial pressure and our initial volume. And then we have our second pressure, our final pressure, and our final volume. Alright, so again, from the very first part of our breakdown here, we know that the balloon was initially at 800 centimeters cubed and 1 atm, which is 760 millimeters per mercury. So we know that our P1, our first initial pressure, is 800 centimeters cubed. And then standard atmospheric pressure, which is our, oh, sorry, I did that backwards. This is our volume. And our P1, our initial, is 760 millimeters per mercury. And then, now, it gives us two different mountains, right? Now, the thing with this is, since we have two different mountains, we're going to have to do two different calculations. So, from our questionnaire, it said that the Mount Everest has an average atmospheric pressure of 221. So, Mount Everest, 221. And for Mount McKinley, it was 345. Okay. Now, the question is asking which balloon will have a larger volume. So we know, for example, P2 for Everest is 221. And our pressure for McKinley is 345. So the information that we're missing is the final volume for Everest and the final volume for McKinley. Now, how do we find the final volumes for each? First of all, we need to isolate this right here, which is the final volume that we're trying to find. So just using a little bit of algebra, we're just going to transfer, we're going to isolate V2 from the rest of the formula. So it's actually going to be P1, T1, all over P2. And that's the formula that we're going to be using right here. Okay. Now it's just a simple matter of plugging in variables. So for Everest, our P1 originally was 760 millimeters for HT. And then our initial volume was 800 centimeters cubed, all over our final pressure, which was 221. And that's going to equal, let me get my calculator. So 760, 100, divide that by 221. And we're going to get 2751.1. Now, significant figures, of course, you always have to count significant figures. Well, it's going to be 3, right? So this is actually going to be 2750 centimeters cubed. And that's the V2 for Mount Everest. Now, the second part, which is going to be McKinley, it's going to do the same thing over here. So 760 again, times the 800, divide that by 345 this time. And for this one, we're going to get 1762.3, but again, significant figures. We should get 1760 centimeters cubed. Okay, now, as you can see here, it verifies with our previous altitude calculation or prediction. We predicted that Mount Everest is going to have the larger volume. Again, from what we said before, as altitude goes up, pressure goes down, volume will go up. Now, our calculations prove that. Here we have our volume of the balloon at Mount Everest, and then the volume at Mount McKinley. So you can see, obviously, that this has a larger volume. Okay. And that's question 1. Now, question 2 is pretty much what I've already explained. So question 2 states, explain why the climbers of such tall mountains need to carry oxygen with them near the top, and how does this relate to low pressures as described above. Now, save on paper here. As I've already stated before. Question 2. Now, as altitude goes up, pressure goes down. This is because of the amount of air on the top of your, current elevation. So, from Boyle's law, from the previous, we know that Mount Everest is high. So as altitude increases, the pressure decreases and the volume goes up, which is to here. At a lower elevation, you have more air above you, so you have more pressure. At a higher elevation, there's less air, so there's less pressure. So that's why they need more oxygen. Once you go higher, there's less air. So you kind of need air. So that's question 2. moving on to the next question. Question 3. A 50 milliliter soap bubble is blown at standard pressure. When a thunderstorm passes later in the day, the pressure becomes 700 millimeters of mercury. Will the bubble get bigger or smaller? What is its new volume? Okay, so let's choose a different color here. And we're still using Boyle's law. We're going to be using Boyle's law all the time. So, remember Boyle's law states that the initial pressure, the initial volume, equal the final pressure, and the final volume. Now, let's break down the question here. So the balloon, or soap bubble, sorry. So we have a soap bubble. That's at 50 milliliters at standard pressure. Now remember, standard pressure, no, I did it again. Standard pressure is, let's see, 760 mercury. Okay, now later, as the thunderstorm passes, the pressure, which is our final pressure here, is going to drop down to 700 millimeters per inch. Okay. Now the question was, will the bubble get bigger or smaller? This is again going back to what I was saying about inverse proportions between pressure and volume. So basically, we've answered this question already. The bubble gets bigger. And why is that? Because when we see here the pressure, the initial pressure was at 760. The pressure went down for the final. So that means the volume went up. That's our prediction anyways. So we're predicting that the volume will get bigger. Now, what is this new volume? So we're looking for the final volume. And again, we're going to manipulate the formula so that we can isolate this right here. So, same one as we used last time. Okay. Now let's figure this out. Just plugging it in. 50 mLs. Now 760. And divide that by 700. Okay, so calculating that really quick. Oops. Oh dear. I'm having issues with my calculator. Divide that by 700. And we should get 54.29 if we're rounding. Now again, significant figures is always going to be the issue here. Oh, rounding. It's going to be 54.3 mLs. Okay. And that's your answer for your volume. As you can see, it did increase. So it was, the bubble was originally at 50 and then went up to 54, and that correlates with our prediction that the bubble would get bigger because the final pressure was smaller than the initial pressure. So they're inversely proportional, which means they're opposite. Okay, and then we know that the bubble got bigger. Okay, so that's number number 4 is pretty much the same exact question, except we're just going to be using different units. Okay, so number 4. Now let's use a different color. I like using different colors. Let's use this one. Number 4. So now we have a balloon. Again, with a balloon. That's inflated to a volume. So our initial volume is going to be 5 liters. And it's going to be at a pressure, initial pressure, of 0.90 atm. Now that's at standard atmospheric pressure. It's pretty close. It rises, so this balloon goes up, and it rises to an altitude, that word altitude again, so to a final volume of 25 liters. Okay? Now the question is asking about the pressure now. Will the pressure on the balloon increase or decrease? Now, Boyle's law, I'm going to keep on repeating this until you're tired of it, states that initial pressure and initial volume is equal to the final pressure and the final volume. Now this is different, kind of, because now we're looking for a different variable. Same thing though, we want to isolate this one now. So manipulating the formula. There you go. And we just plug it in. But before we do that, I'm going to keep on saying this over and over again until we get this. Remember that when altitude increases, pressure is going to decrease, and volume, because it's the opposite, is going to increase. So as pressure decreases, volume increases. So from here you can see that our initial volume was 5, and our final volume goes up to 25. So with that in mind, since our volume went up, that means our pressure went down. That's our prediction. So we're gonna have to test this. Okay, so well, let's plug it into the formula so we can see. So our initial pressure, 0.9 atmospheric pressures, times our volume, divided by, so our new pressure, our final pressure is going to should be less because of what we've been stating constantly now. Let's check. Okay, so our new atmospheric pressure is 0.18. And that makes sense, right? It went down from our initial. Okay, so our next question, question 5, still going to be a little bit different. And we're going to keep repeating the same exact thing over and over again. Boyle's law. By the end of these problems, you're going to have this memorized, hopefully. Okay, now this is question 5. So question 5 states, a scuba diver inflates a balloon. It's another balloon. We're never gonna get rid of the balloon. So this time we have a balloon. And it's inflated to 10 meters. Okay. At the surface. So we've got surface, which is 1 atmospheric pressure. And then at a as the scuba diver takes it on a dive, so it's going down this time. So at a depth of 100 feet. Now see, they're gonna keep tossing you these random numbers. Don't let it confuse you. Always just stick to the variables that you know. Sometimes it's going to have an you know, you're gonna have a reason why, but right now we just know that so they're going down sea level at this point. So this is opposite. Usually we're going with higher elevation. Now we're going in opposite direction. So at a depth of 100 feet, the pressure, so we have pressure 2, is gonna be 4 atmospheric pressures. Now it's asking again. We're going to be looking for our final volume. Will the volume of the balloon increase or decrease, and what was the new volume of the balloon? And again, I'm always going to be repeating this over and over again. As altitude changes, right? This time it's going to be different, but let's repeat what we've been saying. As altitude goes up, pressure goes down, volume goes up. Now, opposite, if altitude goes down, that means pressure is going to go up. That means pressure is going to go down. Okay? Everything is inversely related to the pressure. So, since we're going opposite here, since the altitude is going down, we know that the pressure is going to go up. So we can predict that the volume should decrease. Okay? So to answer the will the volume of the balloon increase or decrease, we're going to predict that it decreases. Okay? Now let's find this out by doing our calculations. Again, we're just going to be manipulating the formula to find this right here. So P1 V1 over P2 equals the final volume. Now we have 1 atmospheric pressure because it was at the surface, standard, and then we're going to multiply that by the initial volume of our balloon, divide that by the pressure that's 100 feet below surface level, which is 4 atmospheric pressures, and then let's just do the calculations really quick. So 1 times and we have 2.5 liters. Okay, and since that's what we predicted, that since our pressure went up, we predicted that the volume would go down. So it matches, right? So our initial was 10. It went down to 2.5. There you go. Okay. All right. Just moving along here. Number 6. Oh, that's a bad color. Let's try for deeper green here. Or not. Alrighty, so number 6. Okay, so the living quarters of the space shuttle has a volume of 20,000 liters. Again, before we do that, I'm going to repeat this and repeat it over and over and over again. You're going to be sick and tired of this, as I am. Okay, so let's break down the problem here. The living quarters of the space shuttle has a volume of 20,000 liters. Okay, So we have our initial volume. And it's gonna be 20,000 liters. It gives us the scientific notation there. But, I mean, I'll put in, no, it's not. Too many numbers will confuse you, so we're going to just keep it simple. 20,000 liters. And it's kept at, so we have that. It's just a different notation, but it's the same exact thing. Okay? If all the air was lost, it would have to be replaced from a compressed air cylinder, which has a volume of 50 liters. Okay. If all the air is gone, now we're going to have a final volume of 50 liters. What is the pressure in that tank? Okay, and that's really straightforward. That's what we're looking for. Okay, now same thing. Always, always, always. It's going to be the same exact thing. We are looking for this little buddy now. Okay, so it's going to be P1, isolating that. Find this, and then just plugging in numbers. So our initial pressure here, we have 12. Times the initial volume, divided by, and then our final pressure is going to be 4,800 pounds per inch squared. And then significant figures, 4,800. Is that right? Let's check. Yeah, that's right. All right. Okay. It's really straightforward, right? I mean, once you keep doing this over and over again, it's just a matter of just picking out the information that you need from the question. Okay? Moving on. Question 7. Almost done. This camera keeps auto-focusing. I really need to fix that. Okay. Question number 7. And as always, we're working with Boyle's law. This is never going to change for these exercises. Okay? Now this next question is asking, well, back to the space shuttle. Okay? So, back to the space shuttle. The living quarters have a volume of 20,000 liters. That hasn't changed. And this time it's giving us the atmospheric pressure, which is, well, the pressure. It's going to be giving us at 500 millimeters of mercury. Now, a shuttle docks with the space lab, which has a volume of 230,000 liters. Okay, so now it's giving us the final volume, or the other volume, which is 230,000 liters, and no air in it. Okay, what does the air pressure in both become when the hatches open between the two? So same exact thing. It's not going to change. It's asking for the pressure. So what is it? And as always, this is what we're looking for. So P1, B1 all over B2. So it's going to be 500. Oops. Times 20,000 all over 230,000 liters. Okay, so what's the pressure? Let's see. Okay, so it's gonna be about 43.48. But again, significant figures, so we're just gonna have to deal with those. Let's see. Okay, so it's gonna be 40. milligrams. Okay. Yes, sig figs. Significant figures. Never ever forget about that. This was a pain in the butt. Still is a pain in the butt. But that's your answer there. And that's how the worksheet should. Okay. Now this last question bothers the hell out of me because it took me forever to figure it out. Mainly because I haven't taken Chemistry 101 in like years. So next, I like purple. Let's go purple. Okay, last question. Question 8. And as always, we are going to use the same exact formula. Okay. Now the question is stating, a fountain pen, which has a total volume of 2.4 centimeters cubed, is half full with ink at the surface, where the pressure is 780 millimeters in the mercury. Okay, it's giving us a tricky question just from that first sentence. So the fountain pen has a total volume of 2.4 centimeters cubed, but it's half full. Let's make a note of that. Half full. Okay, that's just a side note. Let's remember that. Let's box that up. It's half full. But right now we know that the total volume is 2.4. So that's your volume 1. Okay. And the initial pressure, so our P1 is going to be 780 Hg. Okay. Now, it is put in a pilot's pocket who flies to an altitude, and it's going up. So the altitude is going up here. This is with a pilot. Where the pressure, so our final pressure, is 520 millimeters of mercury. Okay. And it says how much ink leaks out of the pen. Okay. Well, let's focus on what we have so far. So we have our initial volume, our initial pressure, and our final pressures, which means we're looking for a final volume. Okay. I know there's a lot of extra information, but let's focus on what we have. So we have volume 1, 2.4, pressure 1, 780, pressure 2, 520, volume 2, we don't know. Okay. So let's just isolate what we've got. We need to find this. So again, we're always going to be using the same exact things here. For P2. Okay. I'll just plug it in. So we have 780. Our initial volume was 2.4. Divide that by 520. And then we're going to get 3.6 centimeters cubed. Okay, now that's our final volume. Now we know that the total volume is 2.4 and our final volume is 3.6 when it goes up to that pressure. So what we're going to do here is subtract our final volume from our initial volume. And that will give us a more accurate amount of ink in there, okay? So we have 3.6 minus 2.4, which is going to equal 1.2. Okay? Now, so this is technically how much ink we have. However, remember that it said it was half full, okay? Half full meaning half of what we have. So we're actually going to divide this by 2. So since it was half full, how much ink comes out? We only have 0.6 centimeters cubed of ink coming out. Now this took a little bit longer because you had to kind of figure out what the question wants. It wants to know how much ink is leaking out of the pen. But before we can figure out how much ink actually comes out, we have to figure out, okay, work with what the variables that we have, and then, you know, kind of decipher these little clues that it gives us about it being half full and what we know about altitude, pressure, and it's a little bit more complicated, the last one, but as long as you break down the problem, it should, of course I say, it should, it should make sense. But, you know, you kind of have to look at the problem a little bit differently and make notes. All right, so you like I said, making a note of this especially. We know that the total volume was 2.4, but it was half full, so you kind of have to mess with the formula a little bit more. But yeah, that's it. That's all 8 problems of the Boyle's Law worksheet. I hope this made sense. If it doesn't, please let me know. And I'll try to explain it a lot. I'll try to explain it as best as I can. I'm not really good at explaining things. Mainly because, one, I'm already a senior at uni, so it's been a long time since I've done chemistry 101 stuff, so hopefully I explained it well enough and I did the math correctly. If not, let me know. But that's it. Okay, cool. Hope this helps.